Good afternoon to everyone, and I'm sorry for the delay. This is because the exam week has already started at MIPT and the schedule was slightly different, so I had to wait for a while to start the presentation. Today is our last lecture, and this will be devoted to continuation of field effect transistor theory and description of physics. This is, as I already told you, one of the main devices in contemporary semiconductor electronics. What we did on the previous lecture is that we have studied we have seen that the performance of the computational electronic devices behaves exponentially with time, and the number of computations per second per unit cost is growing exponentially, which has been called Moore's law till the end of the 20th century. And the second observation is that the sizes of electronic devices that are used in contemporary circuits are going down and down with time, and this observation can be continued till nowadays, till the current years, and the characteristic feature size is also going down exponentially. And the promise of the lecture was to, of the current lecture, is to correlate the two behaviors which we observe, how the small size means high performance. This is what I promised to do today, but first of all we repeat what we did previously. Usha sir, what you mean by spotlighting the lecture? I hope it's recorded. What did you mean?
Okay, the screen is not wide enough, it's just normal.
Okay, I continue. We learned that the field effect transistor is a two-terminal device which resistivity between two terminals called source and drain can be controlled by the third terminal, which is called gate. Sorry for Russian in this picture, but here is fully English translation. So field effect transistor is a semiconductor device where the resistivity between two terminals is controlled by the third terminal called gate. When there is no voltage applied to the gate, then the field effect transistor has a doping structure that prohibits the flow of electric current. It is like an NPN junction, and at least one of these junctions is blocked every time, and it doesn't permit the passage of current. But when we apply voltage to the gate, when we apply positive voltage to the gate in this structure, then the electrons from everywhere, deep from the substrate, from doped contacts, from metal contacts, are flowing toward the insulating layer, and they form the so-called N channel. And now the PN junctions are kind of erased, and the current can flow freely through this structure. The transistor becomes in the on state. We tried to address several applications. In particular, we have shown that the transistor acts as an amplifier of small signals and a generator of high frequency signals. We have we have tried to develop the most simple theory of field effect transistor, which is based on the Ohm's law and on the solution of Poisson's equation in the simplest possible form. So how can we describe the changes in resistivity when we apply gate voltage? This is quite simple. We can write the Ohm's law in the form like conductivity multiplied by electric field, but the conductivity in turn is the product of mobility mu, elementary charge, and carrier density m. And this carrier density is controlled by applying the voltage to the gate. The more voltage we apply, the higher the carrier density. So we can write the second relation between gate voltage and carrier density. The capacitance per unit area multiplied by the voltage drop between gate plate and semiconductor plate equals the charge on one of the plates of the capacitor. And from here it is seen that the carrier density is approximately a linear function of the gate voltage, when the conditions of validity for this expression will be clarified further. But still, the physics of the gating is that the carrier density is roughly proportional to the gate voltage. So the conductivity becomes a function of gate voltage and approximately a linear function of gate voltage. This is the field effect. Of course, the local potential in the semiconductor layer can vary. And we managed to disentangle this equation. We substituted the sheet carrier density into the expression for current, and therefore we obtain the capacitance per unit area multiplied by mobility multiplied by local voltage difference between gate and channel, and multiplied by the electric field, which is the derivative of electric potential with respect to coordinate. Now I again clarify where does the voltage drop happen. This is the gate layer. This is the doped contacts of N-type. There are metal contacts here, metal contacts here. Here we have the insulating layer, and here we have p-type semiconductor. And here is the inversion layer with the induced density N. So the voltage drop is measured between the gate at voltage Vg and some point of the channel where the local potential is phi. Namely, this voltage drop appears in the capacitor type relation between gate voltage and carrier density. So to get the current, we have integrated this equation from the beginning of the channel located at x equal to 0 till the end of the channel located at x equal to L. And the potential varies from 0 voltage at the source till some finite drain voltage at the drain. After the integration was trivial. Here we got the following current voltage characteristic. Current density is the capacitance per unit area divided by channel length multiplied by mobility multiplied by the product of gate and drain voltages minus drain voltage squared divided by 2. This is the current voltage characteristic of a field effect transistor. Initially, at small drain voltages, it goes linearly according to the Ohm's law, and the slope is also linear in gate voltage. This is as I promised you. But later, the slope is going down, the sign here is minus, and the conduction becomes poorer and poorer. And we have seen that this occurs due to gradual depletion of the channel when we approach the drain. The reason is that the local voltage difference here at the drain is smaller than at the source, so the channel is more depleted with electrons. And the conduction, differential conduction, becomes poorer and poorer. This is illustrated in my plot for the current voltage characteristic. Actually, here it predicts unphysical growth or unphysical decay with increasing voltage, but this is an incorrect prediction of our model because it happens at large drain voltages where the expression for the carrier density predicts negative densities. So here the voltage is so high that our capacitor type relation predicts negative electron densities. This is here it becomes invalid, and this invalidity is simply fixed when we add holes, donors, and acceptors. So strictly speaking, we have to consider all the agents that contribute to the charge when we approach the point where the channel becomes roughly neutral. when the number of electrons is small, we have considered also other agents that contribute to charge, and only afterwards we could get a good IV characteristic. One of the other disadvantages of our model was that it predicts, it doesn't predict the presence of the off state in the transistor. Once again, the equation describing the current voltage characteristic was mobility multiplied by capacitance per unit area divided by channel length multiplied by gate voltage and drain voltage and the quadratic correction. Already at its initial part, where the curve is roughly linear, what happens when gate voltage turns negative? Let us consider the situation with negative gate voltages or the situation with roughly zero gate voltage. Then the theory predicts that the conductivity of our transistor would become negative or zero. So the IV curve would look like that or that. This is not good. This is not good because no object in nature can have a static negative differential conductivity happening at drain voltage close to zero. Otherwise, it could be an infinite source of energy, perpetuum mobile. It cannot happen in nature. So this tells us that the applicability of this simple theory is limited only to large positive gate voltages when the transistor is in the on state. What happens in the off state requires more careful consideration, and we should look in more detail on the electrostatics of our device, especially how the inversion layer and conducting channel is formed. So this part of our lecture will be devoted more to the consideration of phenomena that occur in semiconductor substrate when we apply gate voltage. Moving a bit forward, I would like to show that the true current voltage characteristics look like I show here with the dashed lines. So they move upward and then saturate to almost a constant value. So this is the prediction of the true model, which is based on full consideration of charging effects. Indeed, the current can grow no more when we apply drain voltage very high. To get a more detailed theory of conduction, especially in the off state, we need to consider what happens with the field effect transistor in the direction perpendicular to the gate. Let me remind a bit the schematic, what we are trying to plot here. Here is the gate layer, G, insulator, and initially p-doped substrate. Here are the contacts of source and drain. Now let us try to plot the potential relief that the electron sees in this direction, in the direction called Z. Let us plot the potential energy of electron or its band diagrams. U, potential energy versus coordinate Z. When the semiconductor layer is in equilibrium, then it is p-doped in the bulk, which means that the Fermi level is very close to the valence band edge, and from what we know from the Schottky junction theory, holes start migrating from p-doped semiconductor into metal, there is a depleted layer form where when we have small number of holes and slightly increased number of electrons, and there is a small bending of the barrier to the in this direction, as I have indicated. So this is the same as we had in the theory of Schottky junction between metal and p-doped semiconductor. A hole that would like to traverse from semiconductor into metal sees a potential barrier on its way. And this potential barrier actually prevents diffusion and is responsible for the formation of thermodynamic equilibrium. Now, this is almost what we want, because this is almost what we want to get N-type conductivity in the vicinity of surface. So you see that there is quite small amount of holes, small p density, because this region is slightly depleted from holes and slightly enriched with electrons. Now, how can we intensify this process? We can apply positive voltage to the gate. Applying positive voltage to the gate, we reduce the potential energy of electron at the metal layer, and the potential energy is, the electric potential is continuous, then the potential is reduced everywhere in the semiconductor. So the potential well for electron is becoming deeper and deeper. At some point, the Fermi level for electrons can cross the position of the conduction band, and at some point the density of electrons can become very, very high in this potential well. Of course, here we would not consider the effects of possible quantization in this well, but these effects can be important at low temperatures when the temperature is smaller than the level splitting. And actually I have already told that this inversion layer can be a simplest example of two-dimensional electronic system. But for a while we will limit ourselves to nearly room temperatures, when the energy levels can be considered here as a continuum. And we can use a simple Boltzmann type statistic for electrons that have accumulated in this well. Of course, there can be other regimes of gate voltage, like we can apply negative gate voltage, and we can attract holes to the metal surface. And we can apply large negative voltage to attract a large number of holes near the metal surface. And this would increase the hole type conductivity and reduce the electron type conductivity. We will be interested most in the situations like A and B, in the off state and in the on state. Let us try to develop a theory for conductivity in this field effect transistor, which can cover both the off state and the on state. To do so, we actually, if we believe that the conductivity is the carrier density multiplied by mobility and multiplied by elementary charge, all we need is to accurately find the electron density, N. And this electron density should be found everywhere, not only at the surface, but it should be integrated over all possible z coordinates. So actually, to get a conductivity per surface of a field effect transistor, we need to find the surface density of electrons, which is measured in units per centimeter squared. If we know the bulk density dependent on that, then we can integrate it from z equal to 0 to infinity. This would yield us the total density of electrons that was induced here due to the presence of the metal gate. Our next problem that we are to solve here would be to find the distribution of electron density with respect to the coordinate in this structure. Could somebody give me an advice how we can do it? Does anybody remember the type of equation that we will need to solve? Okay, I hope you remember, but you are shy to tell about it. This is the Poisson's equation. The Poisson's equation is the one that relates the derivative, or the second derivative of electric potential to the total charge density in the structure. Here we have it in the distributed form. We don't reduce it to some type of capacitor formula, so we will need to solve it fully and exactly. The exemplifying band diagram is shown here. Можете, пожалуйста, сфокусироваться побольше, потому что формула будет. Меня не надо, вот на слайд побольше и стены не захватывать. Okay. The dependence of electron and hole densities on the coordinate can be neatly expressed as a dependence of electron density on the potential, which in turn depends on the coordinate. And this is an implicit function of the coordinate. We do the same for holes, for which the dependence on electric potential is also the Boltzmann exponent with the opposite sign. M infinity and P infinity are the electron and hole densities deep in the bulk. They are related to the acceptor density by the neutrality condition. N infinity plus acceptor density minus pi infinity equals to 0. This is the first condition, and the second one is that the product should be equal to intrinsic carrier density squared. This enables us to find the hole and electron density far away from the junction, but approximately the hole density in the doped semiconductor equals the acceptor density, while the electron density is very, very small. This is roughly intrinsic carrier density divided by the density of charged acceptors. So we probably started to solve this equation in the previous seminar. To do so, we introduced a new dimensionless potential, which is potential measured in units of temperature. We have rewritten this equation in dimensionless form, and it looked like that. 1 divided by screening length squared, and here 1 plus n infinity divided by acceptor density, and minus p infinity divided by acceptor density, exponent with opposite sign. Where the physical meaning of Ls is the screening length. It equals, it is given by the expression on the lower part of the board. It is inversely proportional to the density of acceptors, square root, and proportional to the square root of the temperature. It is given here in two types of units, in Gaussian units and in the C units. To cope with this equation, we have multiplied it by phi prime and integrated once. This is the common approach for differential equations that do not depend on coordinate, that don't have coordinate z in explicit form. After we did so and integrated it once, we have obtained a nice relation. Phi prime squared divided by 2 in the limits from 0 to plus infinity equals 1 divided by screening length squared multiplied by minus phi plus m infinity divided by scepter density multiplied by 1 minus exponent to the power of phi plus p infinity divided by na multiplied by 1 minus exponent to the power of minus phi. That is all. And this is the result of integrating this equation from some observation point 0 to the other to infinity. And this is a typical trick that is done when solving the differential equations that do not contain coordinate. You may probably have some analogies with the oscillation equations for simple oscillator like pendulum, which is initially based on Newton's law. It is also a second order equation. Then you can multiply it by velocity and pass to the energy conservation form. So this is almost what is done here for the case of the Poisson's equation. And the last step upon solution is that we now know how the electric field, electric potential derivative, depends on potential itself. This is not yet a solution. We would need to integrate it once more in principle to get the full dependence of potential on coordinate. But this is too cumbersome and we won't actually need it. All we need is to express the electric field, which is the derivative of electric potential with respect to coordinate, versus potential itself. Just take the square root of the right-hand side and take the correct sign. If the gate voltage is positive, then the slope of potential energy is positive, while this electric field, while for electric field we should take the opposite sign, because electric field equals minus derivative of potential with respect to coordinate, while potential energy is minus elementary charged by potential. The last expression can be used as a boundary condition for our equation. How we can formulate the boundary condition here? The boundary condition is formulated as the continuity of displacement vector upon the metal semiconductor boundary. It tells us that the dielectric constant of insulator multiplied by derivative of potential with respect to coordinate at insulator side should be equal to the dielectric constant of semiconductor multiplied by derivative of potential with respect to coordinate at semiconductor side. The derivative at the semiconductor side was found, but the derivative at the insulator side can be also found easily, because here the field is constant and the field can be estimated as the gate voltage minus potential at the surface of semiconductor divided by divided by insulator thickness. So what we get finally is the boundary condition for the Poisson's equation. The derivative of electric potential at semiconductor side equals the ratio of the electric constants multiplied by the voltage dropped at the oxide side. This is a transcendental equation with respect to electric potential at the surface. It has to be solved numerically, but its numerical solution is accomplished quite easily. I did it at home for some typical density of electrons in the semiconductors. So here I used the oxide or insulator. This is the same in my notations. Oxide thickness of 100 nanometers and the acceptor doping density of 10 to 17th units per centimeter cubed. So what we see here, how the potential at the surface behaves when we apply the gate voltage. Initially it is linear, but it increases rapidly until strong screening by electrons start. And here something strange happens. Its increase is becoming slower and slower. So initially almost linear rapid growth and then slow growth. Actually, this moment corresponds to the case when the inversion layer starts forming. What does it mean, inversion layer? Inversion layer means that the density of electrons near the surface of semiconductor becomes comparable to the density of majority carriers in the bulk. It means that very large number of electrons has appeared near the surface, and they, once appeared, they induce strong screening. What you also see from the plot, if you look at the numbers, is that when we apply quite large gate voltages, like 10 volts, then the surface potential is much larger than, or much smaller than the applied voltage, order of 0.8 volts. It means that the voltage drop at the semiconductor is typically much smaller than the voltage drop at the insulator. So for example, we apply 10 volt altogether, and 9 of them roughly drops on the oxide side and 1 of them drops at the semiconductor side. But this is not a very general rule, and actually when we make very thin oxides, then this tendency starts to change. So if we make a very thin oxide, then the voltage drop at the oxide can become smaller. Now, how can we use the plot further to find the carrier density? Let us see what we can extract more from this equation. If we know the surface potential, we can also find the bulk density at the surface. Let us try to look at the density at this point in the vicinity of the insulator. This is another plot that I have prepared. This is the electron density at the boundary. When we apply negative voltages and when we apply small positive voltages, then it is very small. It is actually exponentially small, which would become clear from the other plot. And then, at some point, it goes rapidly up. This go up is, again, almost linear, well, with some minor exclusions. Let us see on the same plot in the log scale. the density, the electron density at the surface at intermediate voltages, when we just turn the transistor on, goes exponentially, which means that electron density in the log scale looks like a line, a straight line. And then it has a tendency to a slower growth. In the normal coordinates, it was like a linear function, and in logarithmic scales, it looks like almost saturated. Here I have two indicator lines. The green indicator line is the electron density deep in the bulk. It is indeed very small. It is indeed very small, and when we apply negative voltages, we deplete the surface more and more. And when we apply positive voltages, we enrich the surface. And at some point, the density of electrons becomes comparable to the density of acceptors and the density of holes deep in the substrate. And at this point, actually, transistor gets into its own state. The number of electrons becomes high, and they start screening the external potential quite strongly. I think you can make also this numerical solution by yourselves and see all these fascinating phenomena of enrichment and inversion layer formation by yourself with simple numerical calculation. But this is not everything. Here I show you the electron density per unit cube, like volume electron density per centimeter cubed. To get the conduction of the transistor, we need to count for all electrons that have approached the surface, and they are measured in units per centimeter square per surface. So we will need to integrate the number of electrons from all points, not only at the surface itself. To do so, it may look tricky. It may look tricky because we have resolved the Poisson's equation only until we know the derivative electric field versus potential itself. And to get the full density of electrons, we need to take this Boltzmann distribution with electric potential and integrate it with respect to the coordinate. It looks quite well, it requires much numerics, but we can proceed almost analytically in this case when we replace, this is a very interesting trick. What we know is the dependence of field as a function of potential. This is a simple function that is given here, and we need to calculate the full density. To do so, we express the differential of coordinate as differential of potential divided by electric field. And we replace the electric field with the known function. It actually equals delta phi divided by a known function from one-fold integration of the Poisson's equation. And now this expression expression under the integral sign depends only on the potential. And this is a one-shot integration using any mathematical package that you know. Of course, you should know the limits where the potential changes. But the potential changes from phi approximately equal to 0 at infinity till the potential at the surface phi s. The results of numerical calculations are shown again here on my plot. This is already the surface density per centimeter squared. Initially, it is very, very low until the inversion layer starts. And then it is linear. and then it is linear, so you magnify the gate voltage by 2 times, you get 2 times larger surface density. Here, for comparison, I have plotted the dashed line, which is a simple law that we used previously in our approximate theory. It is the surface density proportional to the areal capacitance multiplied by the gate voltage. You see that the slopes of the curves are almost identical, but the only incorrect thing from our theory is the shift of the curve. So our theory, our old theory, doesn't predict a range of gate voltages that corresponds to the off state of the device, but it can be fixed in almost one phenomenological step. The incorrect equation can be, we can add some threshold voltage corresponding to the switching on of the transistor that places the approximate theory to the true theory, Vt. In experiments, Vt is typically measured, like you apply the gate voltage until your transistor starts conducting well. In theory, it can be also estimated, like you can calculate the density of electrons at the surface and find a moment, a gate voltage, at which this density becomes close to the density of majority carriers in the bulk. This is approximately the threshold voltage. When we look at the induced surface density in the log scale, we see 2 important parts. The on state corresponds to a gradual increase of induced density with respect to the gate voltage, while the off state corresponds to the exponentially small surface density, which means exponentially small conductance. Let's try to compare the 2 scales. Here, in normal scale, you don't see anything at small voltages and you see a line at large voltages. When you go to the logarithmic scale, you notice that this nothing is actually not nothing, but it's an exponential, but exponentially small amount of charge carriers. And then the line looks like a saturation in the logarithmic scale. And you can also try to estimate the slope of this line, and you will get an important fact that the slope of this line, delta logarithm of surface density with respect to the gate voltage, is always smaller than E divided by kT, where E is the elementary charge and T is the temperature. So this switching off of the transistor typically obeys the Boltzmann type law and is limited by elementary charge divided by thermal energy. I would like to, if some of you didn't catch the formulas, I will try to give an intuitive picture of why the transistor goes into the off state, because it may be more important to understand this compared to remembering the formulas. When the transistor is in equilibrium, when no voltage is applied to the gate, then we have N-type contacts, N and P-type channel. When we apply small drain bias, the electrons would like to go here from source to drain, but they see a large barrier at the PN junction. When we apply positive gate voltage, we make an inversion layer, we enrich the channel with electrons and reduce the height of the barrier so that larger number of carriers can jump over it. Of course, there are other situations, like we can apply negative voltages corresponding to these dots, and this would correspond to increased height of the barrier. And then the current and conductance would be exponentially suppressed. Actually, this process has very little probability. I believe some of you are experimentalists working with 2D materials because there are many students from 2D materials departments, and maybe some of you worked with graphene-based structures and measured the conductance versus gate voltage and seen something different. In graphene-based devices, you had an increase in the conductance at negative gate voltages also. Is anybody familiar with that? And probably if not, can somebody suggest why in several kinds of transistors the conductance goes up both at positive and negative gate voltages, while in typical silicon transistors it goes up only at one polarity? This is actually clear from the diagrams that I have plotted here.
Probably graphene doesn't have a band gap.
And what does it lead to? It's a good observation, but how the band gap is related to the conductance?
So when we have a negative gate voltage, we don't have to tunnel, so the conductance increases again.
Yes, it's a great answer, and it is very clear from the band diagram at large negative gate voltage that I plot here. The barrier is really high, but there is another opportunity for the charge carrier to run to the drain. It can start from the source, transfers quantum mechanically through the band gap and get into the valence band, and then travel here and tunnel again. So there are two steps corresponding to tunneling. And if tunneling is possible, like the semiconductor has a very narrow gap or it is very short channel, then the conductance can be increased again at negative gate voltages due to tunneling. But this occurs only in narrow band materials and narrow gap materials, or in very, very short channel structures where the tunneling can be. Okay, I think there is little time for us to get what I promised initially. We will want to estimate the performance of the transistor, which means at which maximum frequency can it operate. There are two types of such estimate. First of all, we would like to know the switching time of the transistor. Like initially it was at 0 gate voltage. Now let us abruptly apply positive gate voltage. Which time does it take to form an N-type channel? This is the first possible formulation for the problem of performance. The other possible formulations deals more with analog electronics, and it asks what is the maximum amplification frequency in the amplifier or generator. So we can try to plot the current gain versus frequency f, and see the frequency at which it drops, for example, by a factor of 2. And this would be the maximum amplification frequency. Both approaches give very similar estimates. The simplest, I will do the first just with Newton's mechanics law. Let us assume that initially the channel was empty and you apply rapidly a pulse of positive gate voltage. Then to form an n-type channel, an electron has to travel from the contact at least to the middle of the channel. So they should travel from here to here and from here to here. The source is, for example, grounded, and it is located at phi equal to 0. The field lines in the transistor would be like that. They would start and end at the source and gate, and the electric field would be directed roughly like this. So the electric field would have a longitudinal component that drags the electrons and the transverse component that ends at the gate. So how we can estimate the time that electron needs to travel at least half length of the channel? It is the channel length divided by drift velocity and divided by 2. What is the drift velocity? Drift velocity is mobility multiplied by electric field. But how can we estimate the electric field? Electric field is the voltage drop divided by the length. So we get that it is channel length squared divided by 2 mu Vg. And here we have the factor of 4 because electric field is roughly Vg divided by 2 channel length. This is just from the picture. Voltage drop is equal to the gate voltage, and the length is roughly channel length divided by 2. So what we get from here is that at fixed operational voltage, at fixed voltage that we apply to switch the transistor between on and off, the time for switching is proportional to the length of the channel squared. And it means that the shorter is the device, the smaller time it needs to switch between on and off, and it means higher performance. So we reduce the channel length by a factor of 2, and we reduce the switching time by a factor of 4. And it is actually the driver for shrinking of the microelectronic devices. The smaller is the size, the shorter is the switching time. And this explains the observed correlation between performance and size. This is the reason why now in electronics, and still now, the size of the gate and of the channel is shrunk and shrunk further, and now it reaches, well, roughly 10 of nanometers in contemporary processors. There is another option to estimate the maximum frequency at which the transistor can operate. It is based on the consideration of analog circuit, where we want to amplify a tiny signal applied to the gate and make it a large signal in the external circuit. Actually, it is based on the comparison of the useful current in the source drain circuit and useless current that is flowing between channel and the gate. This current can flow only at high frequencies and only at large frequencies, because only at finite frequency the insulators allow displacement current. The capacitors become conductive when it deals with high frequencies. So the current that is flowing to the gate at finite frequency is the conductance of the capacitor, which is I omega multiplied by total capacitance and multiplied by the gate voltage, and we can write it in extended form like I omega epsilon epsilon 0 divided by oxide thickness multiplied by channel length and multiplied by channel width. This is the useless current that goes into the drain circuit. Now, what about useful current due to the modulation by the gate? Here we use the IV characteristic in the form current equals conductivity multiplied by drain voltage, but conductivity in turn depends on the gate voltage itself. We have found this dependence, and the conductivity dependent on gate voltage is mobility multiplied by capacitance per unit area divided by channel length multiplied by channel width and multiplied by gate voltage. So we need now to compare the amount of amplified current in the source drain circuit to the current in the gate circuit. Taking the variation of this expression, we get mobility divided by channel length multiplied by epsilon epsilon 0 per oxide thickness multiplied by the width multiplied by the drain voltage and multiplied by small variation of gate voltage. So now we equate these two currents. When these currents are equal, it means that the transistor operation is useless. Like we have parasitic current equal to the amplified current in the source drain circuit. And it means that the transistor has almost lost its gain property. So when we equate these two, we have large cancellations. Width goes away, capacitance per unit area goes away, gate voltage goes away, and for the frequency we get, of course we should take the modulus of these quantities because they are shifted by the phase by pi divided by 2. So we make the maximum frequency equal mobility multiplied by operational voltage divided by channel length squared. Mu Vd divided by channel length squared. By order of magnitude, it is the same as we obtained from simple Newton's law consideration. It means that the maximum operational frequency is proportional to the mobility, proportional to the drive voltage, and inversely proportional to the square of the channel length. Again, you see that the scaling is useful not only for making the conducting channel fast, quickly, but it is also useful to make transistor as a good amplifier. Well, this is actually everything I wanted to tell you.